Here we have a 3 by 3 matrix, and if we want to try this idea of LU decomposition or LU factorization, in both cases, it means the same thing. We just want to split up A into 2 or more other matrices that multiply together to get A. Two or more factors. In this case, for LU factorization, we want specifically 2 factors. And we have a very particular requirement for that. We want to write A as a purely lower triangular matrix called L times a purely upper triangular matrix called U. So the L matrix has to be purely lower triangular. So it can have stuff on the main diagonal. It can have stuff below the main diagonal, but everything above the main diagonal has to be 0. And likewise, U has to be upper triangular. U can have stuff on the main diagonal. You can have stuff above the main diagonal. And some of those might be 0. They don't have to be non-zero. But the requirement for upper triangular is anything below the main diagonal has to be 0. So this is the main idea here. We want to rewrite matrix A, the original matrix, as a completely lower triangular matrix times a completely upper triangular matrix. That's our goal. And this is just one way of factoring a matrix. There's many, I guess you could say infinitely many ways to factor a matrix, to write a matrix as some matrix times some other matrix. And we're going to look at 1 or 2 other very useful factorizations of matrices later on in the quarter. So this is just one example of factoring a matrix. And you can see this to some extent with just numbers also. Like for instance, 30. What's one way you could split 30 into some factors? 30 could be written as what times what?
10 times 3, 15 times 2, 6 times 5, etc.
Yeah, we've got lots of different ways to factor 30. And different factorizations can be useful for different circumstances. Some types of factorizations are unique though. Like if you wanted to split 30 into prime factors, what would that be? If we have the restriction that we only want prime numbers. For instance, the 10 times 3, we could split up the 10 into what?
5 and 2.
Yeah, we could split that up into 5 and 2. So 2 times 3 times 5. Or 15 and 2, the 15 could be split up into 5 times 3, but that's still 2 times 3 times 5. 6 times 5, we could split the 6 into 2 times 3. We still get 2 times 3 times 5. So there's many different ways to factor 30, but there's only one way to prime factor 30. And we're going to see some similar ideas with matrix factorization. There's many different ways to factor a matrix, but if you put in some very specific restrictions, you can narrow it down to only one way to factor the matrix that matches those restrictions. LU decomposition is not actually one of those ways. There are many ways to factor a matrix into lower triangular times upper triangular. But we're going to look at a method of doing that that gets you one specific version of lower times upper. And one way you can do that, we already know one way of turning a matrix into upper triangular. What could you do to make everything below the main diagonal 0? What steps could you take to get rid of everything below the main diagonal?
Just specifically for this situation, or just in general?
In general. Like how would we get rid of the numbers below this one here, the 3 and the 5?
Oh, you can use like elementary row operations, right?
Yeah, exactly. This is essentially a row reduction problem. Although to get it to upper triangular, we don't need to go all the way to reduced row echelon form. We just need to cancel out everything below the pivots. So let's try that. We'll identify the pivots and eliminate everything under the pivots to make the result lower triangular or upper triangular. So first pivot in the first row, We just have this 1 here. You want to use that 1 to eliminate everything under it. So what specific steps would we take to get rid of the 3 and get rid of the 5? What row operations would actually work there?
You can multiply the second row, add 3 times row 1 to the second row.
And I'm going to be a negative there also. So let's say
negative.
Yeah, adding -3 times row 1 to the second row, that will cause the 1 to become a -3 and cancel out the 3 that's already there. And then we can investigate what's left.
Yeah, and then you can also do the same thing, but instead using -5 times row 1.
Yeah. And let's see what we get there. (1, 1, 1) stays as it is. And 3, 3, 1, we got 3 minus 3 becomes 0. 3 plus -3 times 1 also becomes 0. And then 1 minus 3 becomes -2. And then for the next row, we've got a 5. We're subtracting 5 times 1, so we get 0. 3 minus 5 times 1 becomes -2. And 1 minus 5 times 1 becomes -4. And what's our next pivot going to be? This 1 is alone in its column, right? Or not? We don't really need it to be alone in its column. We just need to eliminate everything under the pivot.
So the next pivot, would that be -2?
Yeah. The problem is if we eliminate everything under the -2, then we've gotten rid of everything under the pivots, but the problem is the pivots are now not really in order. It doesn't become upper triangular form. So it looks like this one, it's not actually going to be possible to get it into upper triangular form just by using these elementary row operations, just by adding a row to a lower row. So we're going to need to take one more step. And that one more step, how could you rearrange the rows to get the pivots in order?
What do you switch the rows? Or?
Yeah, let's try switching the rows. So as one final step, we could switch these rows, just swapping rows 1 and 2. And that gives us 1, 1, 1. Row 3 becomes the new row 2, 0, -2, -4. And the old row 2 becomes the new row 3, 0, 0, -2. This is now in purely upper triangular form. So we're going to call this matrix U. That is the upper triangular matrix that we want here. Any questions on that so far? And now to build the lower triangular matrix, one way is you could set A equal to an unknown matrix, like just fill in variables here, like A, B, C, D, E, F, multiplied by this matrix, set it equal to the original matrix A, and then you have to solve for those unknown variables. But that's going to end up having to solve for 6 unknown variables, and that's a huge hassle. So instead, what we can do is we can build matrix L by looking at the individual steps we took to turn A into U. And this is where we get into the idea of the elementary transform matrices again. That each of those steps we took, the adding -3 times row 1 to row 2, adding -5 times row 1 to row 3, each one of those steps can be written as a transformation matrix. We took matrix A, and if we do this one step at a time, the very first thing we did to it was we added -3 times row 1 to row 2. But we can write that step as a multiplication. We can write it as a transformation matrix, let's say E, that's multiplied by A. And that matrix is going to be another 3 by 3 matrix that represents that one change. So how could we write out a transformation matrix that represents this one change of adding negative 3 times row 1 to row 2? What would that look like?
Would that be, so like the first row, would that be 1, 0, 0? And then the next row would be negative 3. I think, would it just be 0, 0? Or
0, 0, because we're adding negative 3 times row 1, but what are we adding it to?
Oh, to row 2.
So we do want a 1 times row 2, but we're not taking any information yet from row 3, so we would put a 0 here. And
Gotcha.
these numbers, the way I generally interpret these transformation matrices, each row of the transformation matrix is instructions on building that row in the result. So this 1, 0, 0 here, the top row tells you what to do with the rows of A to build the new first row. And note that we're not actually making any changes to the first row, at least not in this step. So what we want to do to build the new first row, we're taking the original first row exactly as it is and adding nothing from row 2 and adding nothing from row 3. So this 1, 0, 0 literally just means take 1 times the first row plus nothing times the second row plus nothing times the third row. And the reason this works, if we actually write out matrix A in terms of its rows, if you think of this in terms of the rows individually, when you multiply this out, you're combining a row and a column. So that's 1 times something from the first row plus nothing plus nothing. Then 1 times something else from the first row plus nothing plus nothing. And then 1 times something else from the first row plus nothing plus nothing. So this 1 is getting multiplied in turn by everything in the first row. And these zeros are being multiplied by everything in the second and third rows. So this is literally just saying take 1 times the entire first row plus nothing times the second row and nothing times the third row. In other words, keep the first row exactly as it is. That's your new first row. But what is this second row saying to do? For instance, what is this negative 3 getting multiplied by?
The negative 3 is getting multiplied by everything in row 1.
Exactly. As we combine this row and each column, the negative 3 gets multiplied always by something from the first row. And likewise, this 1 gets always multiplied by something from the second row. And then 0 times something from the third row. So this row could be interpreted as a recipe or a set of instructions saying, take negative 3 times the entire first row plus 1 times the entire second row plus no information from the third row. I like to think of this in terms of instructions on how to combine the information. Negative 3 times all the information from the first row combined with all the information from the second row exactly as is, but taking no information at all from the third row. That's your new second row. Likewise, we're not yet making any changes to the third row because I want to treat these two changes separately for now. If we're not changing the third row at all, what should the third row of our transformation matrix be? If we just want to keep the third row exactly as is for now.
Zero, zero, one.
Exactly. 0, 0, 1. That's saying take no information from the first row, no information from the second row. Multiplying by 1 just means we're taking the third row exactly as it is. So the third row is not changed by this matrix. The first row is not changed, 1, 0, 0. The third row is not changed because 0, 0, 1. But the second row is not really multiplied by anything other than 1, but we're adding negative 3 times the first row to the second row to build the new second row. So this would be our elementary transform matrix. And note that this is almost exactly like what other matrix?
The identity matrix?
Yeah, this is almost exactly like the identity matrix. It just has one small change. because this matrix, this transformation has the effect of making one small change to the result. We're using the first and third rows of the identity matrix because we don't want to change the first and third rows of A. We're just making one small change to the second row of the identity matrix because we want to make one small change to matrix A itself. In fact, an alternative way to build the transformation matrix is to start with the identity matrix, exactly, and then apply this change to it. If you just take this exact same change but apply it to the appropriate identity matrix, adding -3 times 1 to 0 to get -3, and then no change to anything else, it should be a 1 there, then what you get is the elementary transform matrix. So this is another way to build the elementary transform matrix. Start with the identity matrix and make this change, that same change, to the identity matrix itself. What we now have is a matrix we can use to multiply by A to turn it into the next step in the row reduction process. So let's call that matrix, let's just call that E1 for now, in the sense that it's the first elementary transform matrix we're using. You might also see that labeled with 2 subscripts. I think it's going to be called E sub 2, 1, because we're looking at second row, first column as the one change that's being made. But I'm just going to call this E1 for now because it's the first transform matrix we're using. But then what's our next step? We take what we have, and then what's our next operation we're doing to it? We used row 1 to modify row 2. We're also going to use row 1 to do what else?
Modify row 3.
Yeah, we're going to modify row 3. So we're going to put in another elementary transform matrix, which I'm going to call E sub 2. And that's going to look exactly like the identity matrix, except for one modification that does this. So what would you expect that matrix to look like? Which rows are we not changing at all in this step?
1 and 2.
Right, we're not changing rows 1 and 2 at all. We already changed row 2, but this is talking about just the next step. No changes to rows 1 and 2 means we're going to use rows 1 and 2 of the identity matrix. 1, 0, 0 means don't change row 1 in this step. 0, 1, 0 means don't change row 2 in this step. But we are changing row 3 by adding -5 times row 1 to it. So what row 3 would make that change happen?
-5, 0, and 1.
Yeah, that should work. -5, 0, 1. That's saying take -5 times the first row, no information at all from the second row, and add that -5 times the first row to the third row exactly as is. So this row, again, can be thought of as instructions or a recipe for how to build the new third row using the rows you've already got. So that's what we're going to call E2. Any questions on those elementary transforms so far? And the thing is, that didn't quite get in an upper triangular form. We needed one more operation. And what was that one more operation?
To switch row 2 and 3.
Right, and that's going to need another type of transformation matrix. The elementary transform matrix we've been using don't really work here because we're no longer adding a row to another row. We're specifically swapping rows around. So that's going to require a different type of transformation. And that is a transformation called a permutation. So we'll need a permutation matrix. Permutation just means rearranging what you've already got in this context. So to create the permutation matrix, let's call that P. What are we not changing in this step? We're swapping some rows around, but what row is not changing?
Row 1.
Yeah, we're not changing row 1 at all. So we use row 1 of the identity matrix exactly as it is. But we are swapping rows 2 and 3. So what do you get if you swap rows 2 and 3 of the identity matrix?
Would row 2 be 0, 0, 1, and then row 3, 0, 1, 0?
Yeah, that should work because that is just the identity matrix with rows 2 and 3 swapped. And what that's going to do is it's going to say, take row 1 and add nothing to it. That's your new row 1. But note what this is saying. This is saying take nothing from row 1, nothing from row 2, take row 3 exactly as it is, but that's your new second row. So the old row 3 becomes the new second row. And the instructions for building the new third row are take nothing from the first row, nothing from the old third row, but take the old second row exactly as is, and that's your new third row. So you can think of this as the identity matrix has had the rows swapped, so that's just going to swap the rows of the result. You could also think of it as each row tells you instructions on how to build the new row. Any questions on that so far? And more specifically, we would usually call this P sub 2, 3 because it swaps rows 2 and 3. So what we've done then is we've started with matrix A. We left multiplied by E1, the first elementary transform matrix we used. Then we took that and left multiplied by E2, the next elementary transform matrix we used. Then we took that result and left multiplied by P23, the permutation matrix. And the result of all of that is an upper triangular matrix. So we now actually have an equation linking A and U together. Any questions on that so far? Of course, what we actually wanted, we didn't want a bunch of stuff times A equals U. We wanted A equals something times U. So what we need to do is get rid of all these terms one at a time. So we have A isolated on one side. And how would you do that? How would you start isolating matrix A here? What's the first part you need to get rid of? What was the very last operation we did here?
The permutation.
Right, that permutation, the P23 matrix was the last thing we did. So that's the first thing we need to get rid of. And we can do that by left multiplying both sides by the inverse. We have P23 times E2 times E1 times A equals U. We can get rid of P23 by left multiplying by the inverse matrix. P23 inverse on both sides. That way these should cancel out and we're left with E2 E1A equals P23 inverse times U. And there's a very fortunate thing we can use here, a very fortunate fact. P23 represented swapping rows 2 and 3. What's the opposite of swapping rows 2 and 3? What would get you back to the original?
Swapping 3 and 2.
Right, but 3 and 2 and 2 and 3 is the same thing, right?
Oh.
If I swap rows 2 and 3, and then I swap rows 2 and 3, I put them back in these starting places, right? So if you have a permutation matrix, if all it does is swap 2 rows, its inverse is just itself. The inverse of this permutation matrix is just itself. And you can check that. How can you always check if 2 matrices are really inverses of each other?
You multiply them together and they should probably, I think, equal the identity matrix.
Exactly. Their product should be the identity matrix. If we check that, so 1, 0, 0, 0, 0, 1, 0, 1, 0, multiplied by itself. But remember, this is a permutation matrix. All it's going to do is swap rows 2 and 3 of the other matrix. If we swap rows 2 and 3, first row stays the same. Old third row becomes new second row. Old second row becomes new third row. And the result is the identity matrix. So this is a very useful property of any permutation matrix, at least any permutation matrix where all it does is swap 2 rows. If the only thing a matrix does is swap 2 rows, then its inverse is itself, because swapping those same 2 rows again puts it back where it started. So we don't even need to write to the -1 power here. The inverse of P23 is P23 again. Any questions on that so far? And for a more complicated permutation matrix, like let's say it does something more than just swap 2 rows. Let's say you have a permutation matrix that like moves the first row down to the second row, moves the old second row down to the third row, and moves the old third row up to the top. In that case, it won't be its own inverse, but if you multiply it by itself enough times, you eventually cycle back to the identity matrix. It just may take more than 2 steps. So for any permutation matrix, either it is its own inverse, or you multiply it by itself enough times and you get the inverse of the original. Any other questions on the permutation matrices? So what's the next thing we need to get rid of here if we want to truly isolate A on one side of the equation?
E2?
Yeah. Once we've gotten rid of the permutation matrix, E2 is now the most recent thing we did, so it's the next thing we need to undo. So we want to get rid of E2, and we can do that by multiplying by its inverse as well. We multiply both sides by E2 inverse, and this is left multiplying. Order matters here. That is, for each side, we are left multiplying by the same thing, E2 inverse. On the left side, E2 inverse and E2 cancel out. So what else do we still need to multiply by to get A by itself?
The E1?
Yeah, E1 is the only thing left on this side, just E1 times A. So if we left multiply both sides by E1 inverse, again, same operation to both sides, left multiplying by E1 inverse. At this point, ignoring the E2 inverse E2 that canceled out already, we have E1 inverse directly multiplied by E1. So those are also going to cancel out. And we are left with A isolated. A equals E1 inverse times E2 inverse times the permutation matrix, which is its own inverse. So we don't need to bother writing it to the -1 times U. And U was this purely upper triangular matrix. Any questions on that so far? So now let's see if we can invert those E matrices. We know E1 is 1, 0, 0, -3, 1, 0, 0, 0, 1. But note that that just represented one tiny change. That was keeping the first and third rows exactly the same, but just changing the second row by subtracting 3 times row 1. What's the opposite of subtracting 3 times row 1?
Adding it?
Yeah, we could just add 3 times row 1. And this is one of the big advantages of looking at it one step at a time, just looking at a single row operation, a single elementary transform. The inverse of this is going to be exactly the same, but with this -3 changed to a +3. All you need to do is identify that one change and take the opposite of it instead. So E1 inverse is going to be 1, 0, 0, +3, 1, 0, 0, 0, 1. So this E1 inverse, 1, 0, 0, positive 3, 1, 0, 0, 0, 1. And likewise, E2 inverse, the only thing E2 did was a negative 5 here, that is negative 5 times row 1 added to row 3. So we just have to add positive 5 times row 1 to row 3 instead. So E2 inverse is going to be 1, 0, 0, 0, 1, 0, and then positive 5, 0, 1. So those are the inverses of those elementary transform matrices. And one other very important thing about this, how would you categorize these matrices? What do they have in common? Where are the non-zero values here?
The zeros are both in the upper triangular.
Yeah, we've got zeros only above the main diagonal. The only non-zeros we have are in the main diagonal or below. So what do we call a matrix where the only non-zeros are on the main diagonal or below? If the only non-zeros are in this triangle and everything outside that triangle is 0, what category is this?
The lower triangular?
Yeah, these elementary transform matrices are all lower triangular. And the reason for that, all of those represented operations using a higher row to influence a lower row. If all you're doing is using a higher row to influence a lower row or a row even lower than that, then your transformation matrix is not going to have any non-zeros at all in the upper triangle, because you'd only get numbers here, here, or here if you were using a lower row to influence an upper row. But we're not doing that. We're just canceling out stuff below the pivots. So we're only using lower triangular modifications. So because of that, all the elementary transform matrices we're using are lower triangular, and therefore their inverses are also lower triangular. And when you multiply lower triangular times lower triangular, the result should also be lower triangular. In fact, let's do that now. Let's combine those. If we multiply these together, and we could do this row times column, row or dot product, I guess, row dot column, row dot column, row dot column, every possible combination. But a faster way to do that is to use the fact that this is an elementary transform matrix. Start from the left and observe that this matrix means what operation? What was the row operation that this matrix signifies? Or let's put it a different way. What is this matrix not changing? What rows do not get changed at all by this transformation?
The first one.
The first one. 1, 0, 0 says don't change the first row of what's next. So we're going to not change the first row. But note that we also have 0, 0, 1. That means don't change the
Third row.
Right. 0, 0, 1 says don't change the third row of what's next. And the third row of what's next is 5, 0, 1. So we keep the 5, 0, 1 exactly as is. But this middle row, 3, 1, 0, what's that saying to do?
Multiply row 2 by 3 times row 1.
Yeah, or add.
Add.
The second row and add 3 times row 1. So we take the second row, 0, 1, 0, but we add 3 times the first row. So 3, 0, 0 gets added to 1, 0, 1, 0, and we get 3, 1, 0. So that is now a purely lower triangular matrix that represents all these changes signified by these row operations, but in reverse. We still need to deal with the permutation matrix though. And the problem is the permutation matrix, which was 1, 0, 0, 0, 0, 1, 0, 1, 0, is that lower triangular? That is not lower triangular, right? It has stuff above the main diagonal, so this does not count as lower triangular. It also has stuff below the main diagonal, so it doesn't count as upper triangular either. So we can't really bundle this into the lower triangular pieces because it would make it not lower triangular anymore. We also don't want to bundle it into the upper triangular part because it would make it not upper triangular anymore. So we're just going to have to leave the permutation matrix as it is. The E1 inverse times E2 inverse we can bundle together and call that L because that is lower triangular. So L is just the elementary transform matrices multiplied together. The U matrix is just what we got from the result of all the row reduction. But it turns out this A matrix, this original matrix, cannot actually be written as just L times U. We have to have a permutation in order to get these rows to work out in the right order. So instead of writing A as L times U, we're going to write A as L times P times U. So this would be LPU factorization. It's impossible to factor this matrix, this particular matrix, as just L times U, but we can factor it as L times P times U. So the end result of that is going to be our original matrix A equals L, the purely lower triangular matrix we built from E1 inverse times E2 inverse in that order. Times P, the matrix of swapping rows 2 and 3. Multiplied by U, the result of all the row reduction we did earlier. So this would be LPU factorization of that original matrix A. We've got a matrix we're going to call L because it's lower triangular. We've got a matrix called P because it represents the permutation of 2 rows. And we've got a matrix that we call U because it's purely upper triangular. So this is the LPU factorization of this original matrix A. Or I guess I should say it's one possible LPU factorization. LPU factorization is not unique. There are other factorizations that also fit the requirement of lower times permutation times upper, but have different numbers filled in, but still multiply to the original matrix. Any questions on that so far? And there's also one other way you could do this. Instead of factoring it as LPU, you could change the order around and factor it as PLU instead. Of course, you can't just swap these matrices because matrix multiplication is not commutative. Order does matter. But if you wanted to write as PLU instead, you just have to rethink how you did the operations. In the first place, we did some row operations first. Add to this row, add to this row. And then we noticed, oh, we're going to have to make a row swap. But there's no reason we have to do the row swap last. If you do the row swap last, then the permutation is the last thing you did, so it's the first thing you need to undo, so it goes in between L and U in the end result. But if we go back to the beginning, we could say, well, we know we're going to have to swap rows 2 and 3 later anyway. What if we started by swapping rows 2 and 3? That way you do a permutation first. So you could start by applying a permutation to A, and then apply an elementary transform and another elementary transform. They're going to be different transforms though. So let me call those E3 and E4, because those are going to be different from the ones we did by doing the transforms first. But this is certainly a valid way of doing this. You could take the original matrix A, swap rows 2 and 3 first, because in this case, we know we're going to have to do that later anyway, and then use transforms to eliminate everything under the pivots. The result should be upper triangular. In this case, though, what would be the first thing you'd need to get rid of? What's the first piece?
The E4?
Yeah, E4 is the last thing being done if we did the permutation first. So get rid of E4 first by multiplying both sides by E4 inverse. Once we've gotten rid of that, the next thing to get rid of would be E3, working our way in from the outside. So you left multiply both sides by E3 inverse. And then the last thing to undo is, I guess that would still be P23, because we'd still be swapping rows 2 and 3. And the inverse of P23 is just P23 again, because swap rows and then swap them again, you get back to the original. So in this case, we could say A is the permutation matrix. And then these two matrices are both lower triangular. So you could combine them into a different lower triangular matrix than this one, and then multiply by U. So you could split up A into LPU factorization or PLU factorization. It's going to result in the same U matrix because we got both of those just by, well, will it be the same? I guess it doesn't necessarily have to be the same because this factorization is not unique. But you're definitely going to get a different L matrix, and it will still be the same P matrix. It's just in a different order. So you could factor this as LPU or PLU, depending on whether you do the row swap at the beginning or at the end of your row operations. But it's actually impossible to split this into just LU form because you have to do some sort of permutation to get the rows to work out or to get the pivots to work out in order at the end. But that's just because of this specific matrix. If we had used a different matrix, like let's say these rows had been written in the opposite order at the very beginning. In that case, we wouldn't have had to do a row swap. So instead of getting LPU or PLU, we just have lower times upper. So you can get A equals L times U alone if you don't have to do a row swap. If the row operations, just adding a row to another row or adding a multiple of a row to another row, if those work out to upper triangular without needing any row swaps, then that means that matrix can be written as purely lower times purely upper. On the other hand, if you do need a row swap at some point, then you can write it as LPU or PLU, depending on whether you do the row swap at the beginning or do the row swap at the end. Any other questions on that? And again, I want to emphasize that LU or LPU or PLU is just one way of factoring a matrix. There are many different ways you could split up a matrix into two or more simpler matrices multiplied together. We're going to be looking at some more later in the quarter. One of the most important ones is called diagonalization, where you split up a matrix into a purely diagonal matrix, just numbers on the main diagonal, flanked by another matrix on the left and the inverse of that matrix on the right. And that turns out to be one of the most useful ways to factor a matrix for a variety of different applications, especially in differential equations, if you're going to be taking Math 22b later on. But for now, we're just looking at LU factorization or LPU or PLU as one example of how to factor a matrix. And this ties in very closely to all this row reduction stuff, because you're using row reduction to get to U in the first place. The L matrix is just the result of all those row operations written as L matrix transform matrices. So try this out. You can get a lot more practice with this. Basically, any of these systems of equations you were solving using row operations, you can try applying this method to those. Just take your coefficient matrix, the coefficients of X, coefficients of Y, coefficients of Z, and try applying this method to LU factor that coefficient matrix. It should be the exact same row operations you'd use for row reducing to get to the solutions. You just don't need to get all the way to reduced row echelon form, just to upper triangular form. But then write all those operations as a lower triangular matrix. So give that a try, get some more practice. Feel free to contact me if you have any more questions, and I will see you next time.